In this video, we are going to do a partial fractions example that involves long division of polynomials. So I want to begin with a warm-up problem where we divide these two polynomials. But before we do that, let's first quickly go over, well, how did we do long division with just integers? So if I'm doing 17 divided by 3, so 3 goes into 17 5 times. I can put a 5 up here. And then 3 times 5 is 15. Then we subtract. So that gives me 2. And this 2 is what we call the remainder. So that's the remainder. One of the things I can do is this means that 17 over 3 equals this number on top, 5, plus a fraction where the remainder is on top, and the number I divided by is on the bottom. If I were to check this and add these, getting a common denominator, that's the same thing as 17 over 3. So let's try doing this now when I'm dividing two polynomials. So I'm going to first write it in the same way. Let's put the top polynomial here, x to the 4 plus x to the third minus 5x squared. There's no term with an x, so when I'm missing a term like that, I always put it in, but make the coefficient 0. So 0x, and then I have my plus 1. Then I put my division bar, and what I'm dividing by on the outside, x to the third minus 2x squared. The first step when I do this division now with polynomials is I look at the biggest power term out here, the biggest power term in here, and I ask myself, okay, what do I multiply x to the third by to get this x to the fourth? And that would just be x. And I'm going to write that x up top. And I like to place it above where the x term is here. So above where that 0x is, that's where I'm going to write this x up top. Now we multiply the x by this polynomial. So x multiplying x to the third is x to the fourth. And then x multiplying negative 2x squared is minus 2x cubed. And just like with numbers, now we subtract. So I put a minus, I put a big old parentheses around this. So we're doing this whole polynomial minus this one in parentheses. So the x to the fourths cancel. X to the third minus minus, so double negative becomes a plus. So I'll get 3x to the third. And then all these terms just stay there when I did my subtraction. I'll still have minus 5x squared plus 0x plus 1. And then I repeat the process. So now the biggest power term here is x to the third. And over here is 3x to the third. What do I multiply x to the third by to get 3x to the third? Well, I multiply by 3. So I put the 3 up top now. And 3 is constant, so I put it above the constant term that I have here, above the 1. So, and it's plus 3. So 3 multiplied by x to the third is 3x to the third. 3 multiplied by minus 2x squared is minus 6x squared. Now I subtract this away. I put a parentheses around it. When I subtract these two polynomials here, I'm going to be left with x squared. Let me just skip the 0x this time, and then I'll have the plus 1. At this point, we are done because now we have a polynomial whose degree is less than the one that I started with. So once it's less, we are done with this long division. And what we have down here is the remainder. This is the remainder. And just like we did with the 17 over 3, what I can now say is for my polynomial division, this equals the thing on top, which was x plus 3, plus a fraction, where the remainder goes up top, x squared plus 1. And the denominator is whatever I was dividing by. X to the third minus 2x squared. All right, and we have it. So now let's do an example where we integrate this function using partial fractions. Okay. So I first want to recall that when my numerator's degree, which in this case is 4, is greater than or equal to the denominator's degree, which is 3 here, I first need to do long division. We first got to do long division, which we just did. We just did it. And doing the long division, we ended up getting this. So doing the long division, we just got that. Okay, so where do we go from here? So we just did that long division. So now I'm going to be ready to set up my partial fractions for the part of this that's a fraction. So for this x squared plus 1 over, let's factor the denominator. I can factor out x squared, and then I'm left with x minus 2. I'm going to set up some partial fractions for this. So the first factor of the denominator is x squared. That's a repeated factor because it's x and then times another x. So I'll have one fraction where the denominator is x, another fraction where the denominator is x squared. And I would have kept going like that, like x to the third, x to the fourth, up until I reached whatever this power was. All right. And then my numerators, I'll put a up top for this one, and then a different number for the next one, which I'll call b. Now my next factor is x minus 2, so I need another fraction where the denominator is x minus 2. And the numerator of that should be, I'll pick another variable. I'll put c here. So I got my setup. Now I need to simplify this. So to simplify this, I'm going to copy this whole thing down once, and then we'll start to do some algebra on it. So let's copy the whole thing. And I'm going to clear out the denominators by multiplying by x squared times x minus 2. I'm going to do that on the left and on the right. Multiply by x squared times x minus 2. So on the left-hand side, that'll just clear out the denominator, and it'll just leave me with x squared plus 1. On the right, we got to take this whole thing, x squared times x minus 2, and distribute it to each of these fractions. So distribute it to each of these three fractions. So multiplying the first fraction, I'll cancel an x and have ax x minus 2. For the second fraction, it'll cancel x squared, and I'll get b times x minus 2. And for the third fraction, it'll cancel the x minus 2, and I'm left with c times x squared. So we've cleared the denominators. Now my next step is we want to plug in some nice x values. So we want to plug in some nice x values. So nice x values are typically x values that might make some of these factors become 0. So I'm thinking numbers like 0 would be nice. Or maybe x equals 2, because I'm seeing some x minus 2s here. If I plug in 0, on the left side I get 0 plus 1. On the right, this first part with the a will become 0. The part with b will be b times minus 2. And the part with c will also become 0. So if I isolate b, we get b equals negative 1/2. So negative 1/2. That's what b is. So for the b, the numerator of x squared, we're going to write negative 1/2. All right. So what about if I plug in x equals 2? On the left-hand side, we'll get 4 plus 1. On the right-hand side, this a term becomes 0. The b term is also 0. The c term becomes 4c. So dividing 4, I get that c equals 5 over 4. So highlighting this, c is 5 over 4. So this numerator c, the numerator of the x minus 2, I now know is 5/4. There's no other x value that would make any of these factors become 0. So at this point, I just have to pick something else that's kind of small and simple to plug in. So maybe I would pick like x equals 1 or x equals negative 1. So if I plug in x equals 1, on the left, I'll get 1 plus 1. On the right, I get a, which I don't know, times 1 times negative 1. And then I have b, which is negative 1/2. Parentheses, x minus 2. 1 minus 2 would be negative 1. And then it's plus c, which is 5/4, times 1 squared, which is just 1. If I simplify this, I'll get 2 on the left equals negative a plus 1/2 plus 5/4. Okay, and if we rearrange this and isolate a, we get that a equals negative 1/4. So let's highlight that. I'll highlight this in a different color. A is negative 1/4. That's the numerator of x. That is negative 1/4. So at this point, for my fraction, we've done the partial fraction decomposition, and we got that it became this. The x plus 3, of course, from doing the long division, that's still there. I don't need a partial fraction decomposition for that. We know how to do that antiderivative. Okay, so now we have to do the integral of this whole thing. So let's just do that term by term. So antiderivative of x, that's just reverse power rule. That's just x squared over 2. Antiderivative of 3 is 3x. For the next term, the negative 1/4 is just a constant multiplying the function. So I can pull that in front, minus 1/4. And then it's like I have a 1 over x. And that antiderivative is ln absolute value of x. Similarly, for the next term, I can pull the minus 1/2 in front. And then it's like I have that minus 1/2 x to the negative 2. So for x to the negative 2, I can do a reverse power rule on it. And if I do a reverse power rule on it, that antiderivative ends up being negative and then x to the negative 1. All right. One more term. The 5/4, I can pull that constant in front. So 5/4. And the antiderivative of then 1 over x minus 2, I know that because that denominator is linear, it'll still give me an ln. I'll have ln of x minus 2. I should just check that when I do this derivative, would it pop out any extra constants that I'm going to need to adjust in the front? So the derivative of ln of x minus 2, the derivative of ln of stuff is 1 over the stuff. So it would be like 1 over x minus 2 multiplied by the derivative of the inside, which is 1. So because it just pops out of 1, the 1 essentially disappears. So there's no kind of extra constant that pops out that I would need to adjust for in the front. So it's just this. And this was an indefinite integral. So at the end, I need to put my plus c. And we got it. Okay. In the next video, we will do an example where my denominator has a quadratic factor that does not factor. And we'll take a look at what the partial fraction decomposition looks like there.